of partial pressures. In this video, we're going to define mole fraction, partial pressure, and identify how mixtures of gases behave. We'll use mole fractions to calculate the partial pressures, use partial pressures to calculate the mole fractions, and use the ideal gas law and Dalton's law to calculate partial pressures. Let's first start in simple terms. We're going to walk through the basic idea behind Dalton's law. If we have a mixture of gases, the total pressure of the gases is equal to what each gas would be if they were alone added together. We're going to walk through a very generic situation. Let's say that we have a mixture of two gases. We'll call them A and B. If you put just A under a certain set of conditions in an identical container, say that it would be 1 atmosphere. And the same thing for B. Only now, for B, we're going to put it as 2 atmospheres. Now, if those two gases happen to also be in the same container, and so you have that 1 atmosphere of A, but now you combine it with that 2 atmospheres of B in an identical container, our total pressure is 3. So now let's put this into equation form. We're going to do this in 2 ways, and one sort of transitional way. As we discussed in the last slide, the total pressure is the partial pressures added together. And so we're going to write it like this. There's one other useful thing to notice about this. And that is, if we have these pressures, we could do the ideal gas law for part A, for pressure B, and for pressure C. It would look like this. Now, why can we do this? For every pressure given, we could fill in the ideal gas law. But if we do this, then we know that V and T have to be the same. And so we can do something else with this equation. We can pull out the R, the T, and the V, and just leave the N's in the parentheses. This is really convenient because we also know that if we're given the moles of a gas now, many gases, that we can just add them up and fill that into our ideal gas law. And again, that works because our R, our T, and our V are going to be constant if our gases are in one container. So while you don't necessarily have to be able to do this last section to be able to work problems, it does speed it up quite a bit. Now let's talk about another set of equations, or maybe even call them definitions, depending on how you want to think about them. This is very important and is related to mole fraction. A mole fraction is the same as any other fraction. A fraction is the part over the whole, which means that a mole fraction is the moles of one species over the total moles. Think about how we use normal fractions, or in other words, how we use normal percentages. If we use the fraction form of a percent, we can multiply it by the total, and we get the part that we're interested in. The same is going to hold true for mole percent and pressure. Let's say that we multiply the mole fraction by the total percent. We would get the partial pressure of that gas. And that too just comes from the fact that you add up your partial pressures to get your total pressure. So this set of definitions or equations will be very important in our future problem solving. Before we do this with some more complex chemistry, let's look at it very pictorially. In the boxes, we have 10 particles. To make the first example simple, I have said that the total pressure is 10 units. This makes it quick and easy to relate the mole ratio to the total pressure. For the pink diatomic molecule, we can see that there are 3 total molecules. So the ratio is going to be 0.3 because we have 3 out of 10. Now, this also will give us the partial pressure because the partial pressure will be the 0.3, the mole fraction, times by 10. We can do the same thing with the purples, so stop for a minute and do that. Fill in the chi and the partial pressure for the purple. For the purple, we're going to have 4 out of 10 as our mole fraction. This gives us 0.4 as our mole fraction, and it gives us 4 as our partial pressure, 0.4 times 10. Pause again and do this for both the green and the cyan. For green, we have a mole fraction of 0.2, which when we multiply by 10 becomes 2 for our partial pressure. And for cyan, we have a mole fraction of 0.1, because there's only one atom, giving us a total pressure, or a partial pressure rather, of 1. Let's do one more thing. Notice what happens when you add all of these up. 3 plus 4 plus 2 plus 1 is equal to 10. And that's exactly what should happen. Your partial pressure should always add up to your total pressure, or else something has gone wrong. We're going to review in this video what we've learned, and then the following video will have all of our examples. They tend to get very long, and I thought it better to set them aside in a separate video. Partial pressures of each individual type of gas add to equal the total pressure. Or in other words, the partial pressure of A plus the partial pressure of B plus the partial pressure of C, and so on, will add up to be the total pressure. This allows us to alter the ideal gas law a bit into P is equal to all of the moles added together times RT over V. This also means that we can find the partial pressure with the mole ratio by using chi is equal to the moles that we care about, that we're looking for, over the N total. And that the partial pressure is equal to the mole ratio times by the total pressure.